In number theory, a rational point is a point in space each of whose coordinates are rational, that is, the coordinates of the point are elements of the field of rational numbers, as well as being elements of larger fields that contain the rational numbers, such as the real numbers and the complex numbers. For example, is a rational point in two-dimensional space, since 3 and -67 are rational numbers. A special case of a rational point is an integer point, that is, a point all of whose coordinates are integers, e.g., is an integral point in three-dimensional space. On the other hand, more generally, a k-rational point is a point in S space where each coordinate of the point belongs to the field K, as well as being elements of larger fields containing the field K. This is analogous to rational points, which, as stated above, are contained in fields larger than the rationals. A corresponding special case of k-rational points are those that belong to a ring of algebraic integers existing inside the field K. Rational or k-rational points on algebraic varieties. Let V be an algebraic variety over a field K. When V is affine, given by a set of equations Fj equals 0, j equals 1, m, with coefficients in K. A k-rational point P of V is an ordered n-tuple of numbers from the field K that is a solution of all of the equations simultaneously. In the general case, a k-rational point of V is a k-rational point of some affine open subset of V. When V is projective, defined in some projective space by homogeneous polynomials, a k-rational point of V is a point in the projective space, all of whose coordinates are in K, which is a common solution of all the equations. Sometimes when no confusion is possible, we say rational points instead of k-rational points. Rational points that lie on an algebraic variety constitute a major area of current research. For an abelian variety A, the k-rational points form a group. The Mordell-Weil theorem states that the group of rational points of an abelian variety over K is finitely generated if K is a number field. The Weil conjectures concern the distribution of rational points on varieties over finite fields, where rational points are taken to mean points from the smallest subfield of the finite field the variety has been defined over. Example 1. The point is one of the infinite set of rational points on the straight line given by the equation y plus 67/4 equals 2. This set of rational points forms a commutative group with group operation, plus, equals, and group identity. It can be shown that there are no integral points on this particular line. This line is a simple type of an algebraic curve, which in turn is a type of algebraic variety. It should be pointed out that there are also algebraic curves which contain just finitely many or even no rational points at all. Example 2. The point P equals is a point on the algebraic variety given by the equation 3 by 2 minus 2y equals 0. Although P is not a rational point, since the coordinate square root 2 is not rational, P is an F-rational point. If F is chosen to be the field of numbers of the form a plus b square root 2, where a and b are arbitrary rational numbers. This is because the coordinate square root 2 equals 0 plus 1 square root 2, and the coordinate 3 equals 3 plus 0 square root 2, and the numbers chapter 0, 1, and 3 are rational. Example 3. A point in the complex projective plane is R rational if there exists a complex number Z such that ZR, ZB and ZC are all real numbers. Otherwise it is a complex point. This description generalizes to complex projective space of higher dimension. Rational points of schemes. In the parlance of morphisms of schemes, a k-rational point of a scheme X is just a morphism spec Kx. The set of k-rational points is usually denoted X. If a scheme or variety X is defined over a field K, a point XX is also called a rational point if its residue field K is isomorphic to K.